Resolution of forces. Resolving forces means splitting them into component form. This is usually done in the horizontal or I direction and the vertical or J direction, but this is not always the case. Let's suppose we have a force F. Imagine that you're here and that you're being pushed in this direction. We could take this force away and replace it with two forces, one going this way and one going this way, and they would do the same thing as the force F, and these are the components of this force. While this is not always done in the I and J direction, it is usual for these two vectors to be mutually perpendicular, so there would be a 90-degree angle just here. We can split other types of vectors other than forces in this way. Mrs. Smith is pushing a laptop trolley up a ramp with a slope of 10 degrees. She is pushing with a force of 150 newtons at an angle of 20 degrees above the horizontal. We want to resolve this force into components parallel and perpendicular to the slope, and also resolve the force into components parallel and perpendicular to the horizontal. A diagram will help. Let's suppose that this is the slope and this is the horizontal. Then we know that this is 10 degrees. If this is Mrs. Smith, we know that she's pushing in this sort of direction, so that this is 10 degrees. If she's 20 degrees to the horizontal, she's 10 degrees to the slope. And this is 150 newtons. So if we resolve this parallel to and perpendicular to the slope, we're just using trigonometry in this triangle here. So let's call the force F, and we can see that that would be 150 cos 10 in this direction, and then 150 sine 10 in the direction perpendicular to the slope. Now if we consider the situation to the horizontal, then we're resolving this way and this way. The angle now is 20 degrees. So now F would resolve into 150 cos 20 and 150 sine 20. It's worth noting here that I have decided to write this in a column vector form, where in both cases the top number is going to be the parallel situation and the bottom number is the perpendicular situation. You may have decided to notate this differently. Mr. Feith is flying en route to the airport. The wind direction is 30 degrees east of the direction of travel as shown in the diagram below. The wind exerts a force W on the rudder. So since the diagram's going straight up the page, we'll assume that this is north up here. So 30 degrees to the east would be in this sort of direction. And this force is W, and this angle is 30 degrees. So if we just split that into a component going this way and a component going this way, so we're forming this triangle just here, then we can see that this angle's 30, this one's 60. So we could express this one as W cos 60, or alternatively, since this angle's 30, W sine 30. Cos 60 is a half, so that's W over 2. And going this way would be W sine 60, which is W root 3 over 2. So this is the answer to part A, and then in part B we want to calculate the percentage of the force of the wind that is in the direction of travel of the aeroplane. So that's this one here. So we want to express that as a percentage of the total force. W's cancel, so we get root 3 over 2 times 100, and that's approximately 86.6%. What's interesting is if we do the same calculation with this one, we get 50%. So we've got 86.6% acting this way and 50% acting that way. So it seems like we have more than 100%, but they're not acting in the same direction. What we've got is a situation where if we added them, so 86.6% is a decimal 0.866, this one's 0.5, and if we apply Pythagoras here, we get very close to 1 because we've rounded this one. So it does add up to 100%. It just seems strange that we've got more than 50% here and 50% here. Three forces are applied to a single point as shown in the diagram below. We want to resolve the forces into horizontal and vertical components and then find the resultant force acting on the point. So let's call these forces 1, 2 and 3. And let's look at force 1 first. We form a right-angled triangle here, then these are the components we want. So that's going to be 50 cos 60 in this direction, and then 50 sine 60 upwards. Now let's look at force 2. So we want to go this way and this way. This is 70, this one's 20. So we can say that this one here is 100 cos 20, and that would need to be negative because it's going this way, and then negative because it's going downwards, 100 sine 20. And then for number 3, so that's going this way and then downwards, that's 15, this one is 75. So that's going to be 150 cos 75, positive because it's going to the right. Then we'll have negative 150 sine 75. Now for the resultant force. Now that we have these resolved into components in the same two directions, we can just add the components. So we're going to have 50 cos 60, take away 100 cos 20 plus 150 cos 75. Then we'll have 50 sine 60, take away 100, sine 20, take away 150, sine 75. Calculating these, that gives me negative 30.146 and negative 135.790, working to 3 decimal places. So let's look at this actual resultant. So it's going this way and downwards. The third side is the actual vector. So this is negative 30.146. Actually, we'll just ignore the negative because it's negative because it's going to the left. So let's just take the negative out of there. And then we've got 135.790. We know this is a right angle. So, using Pythagoras and working this out, we get 139.1 newtons, correct to 1 decimal place. Working out this angle, and then we'll give it from here, so we'll give it in polar form. So we know that's 180. So work out this angle, add it to 180, and that gives us 257.5 degrees from the positive x-axis. We can now do exercise 4.06 on page 134.